Thank you. Very excited to be here. I will present sitting because I have some demos that I want to click here, but super excited about Signal Shot. Signal Shot is Max vision, and we are really grateful at the Lean Flow that he chose Lean to make it real. I met Max last year. We connected immediately. He even speaks Portuguese. That's my native language. Some people say I'm lucky. I'm a lucky person. Maybe I am. I mean, Lean is a programming language and a proof assistant. It's very extensible. We're going to see evidence. We're going to see many different evidence today for that. It has a small trusted kernel. You can export your proofs, and you can check them with dependency checkers. The Lean Flow, many folks of the Lean Flow are here today. It's a non-profit that Sebastian Uri and I launched almost 3 years ago now. I mean, this summer is going to be 3 years ago. And we have 20 engineers working full-time on Lean, right? The Lean mathematical library, MathLib, has more than 200,000 theorems. And we have CSLib also. CSLib, the director of CSLib is here today, Alexander Ragemaker. And the whole CSLib steering committee is behind the Signal Shots, right? They all want support. And one cool thing, in the previous talk, they mentioned Verso. These slides were built using Verso, right? And every example in this slide is type checked. It's correct. There are no typos anywhere. All examples are perfect because they have been type checked with Lean. Mathematics now, we are really grateful that the mathematical community is embracing Lean, right? You have 6 Fields medalists embraced Lean. You have big projects like the liquid tensor experiments that brought the math community to Lean. And a few years ago, I would use the ABC conjecture as a motivator for Lean, saying one day we're going to settle the ABC conjecture using Lean. And because it has been open for more than 10 years now. And people thought it was a joke. I mean, that we're not serious. I mean, Mochizuki, the guy behind the proof, is using Lean now. I mean, and he says Lean is a tool for communication. It's the first tool he managed to communicate his ideas to the mathematical community precisely without losing information in the process, right? He's doing it now. I mean, he just wrote a big progress report about it. He gave a talk 2 weeks ago about the progress. And why I'm telling you this? Because the Signal Shot needs mathematics, right? I mean, you have cryptography. I think Cedric, I don't know if he's here today. I mean, I saw, oh, Cedric, it's great. Cedric, I remember, I know Cedric for more than 20 years. I mean, and we had dinner last year, and he was saying, praising MathLib, saying MathLib has the right abstractions that made his work much easier. Scaling, but you have the elephant in the room, it's the scaling problem, right? Proof assistants are great because they have a small TCB, a trusted code base, but many people believe that they do not scale as well as tools that have a much larger code base like Daphne and Verus, right? Adam Shipala's group has documented that extensively in many papers. They found similar issues with both Rock and Lean. And the bottleneck is the platform, right? But I said I'm a lucky guy. I'm a lucky guy. I met Andres Urbsen. We had a hackathon that Jonathan Prochenko was organizing at Google. And Andres, during the hackathon, he distilled an example that I want to share with you today, an example that exhibits all the performance bottlenecks that they found in proof assistants. And here is a very minimal example, but it's parametric. You can make it as big as you want. But let's see. This is a small imperative language. You have just 2 operators, binary operators, addition, subtraction. Your expressions, you have literals, variables, and operate. You can have adds and subtract expressions. And for the demo, we need only 4 commands. Skip, right, that does nothing. Assignments, that you evaluate an expression, assign its value to the variable with the given name. you have sequential composition, and you have an input operator to read, and you store the value in a variable. Let's see if I can move this stuff here around. How can I move this?
There's more. I think you go to more.
Where?
When it hovers.
Oh, okay.
I think you have something hide floating meeting controls.
Okay, great, great. And here I'm defining two abstractions: a memory that's a partial map from words to bytes, and a local context that contains the value of the variables, right? The name of the is a mapping from strings, the name of the variable to words. Then we have the operational semantics for this language, right? We have events, only input events matter here. You have a post condition. That's post conditions are predicates on a list of events on the memory and on the local context. And you have our inductive predicate that captures the semantics of this little language. It's basically, you have 5 arguments. You have the commands, the initial set of events, the initial memory, and the local context. And you are claiming if this predicate holds for this quintuple, you're basically claiming the post condition holds, right? And let's get a few examples, like skip. Skip is X going to hold for the skip commands if the post condition holds on the set of events, the memory, and the local context, right? Skip doesn't do anything. But let's see the sets, the assignments. You have a command that you're assigning the value of the expression E to X. You have a hypothesis that says that if you evaluate E on the current memory and local context, you get some V. You may get some V back. If you get a V back, right, the post condition will hold if you can prove that it holds for the same events, the same memory, but in an updated local context where now X contains V, right? And Andre's made the point it's much better to use this version of this continuation passing style version of sec, right? Instead of using the default rule that has this, you would have to come up with this mid post condition. We can use this variant here that we just proved correct, right? I mean, it is much easier to automate your proofs using this theorem. Before we show the example, how to solve the example, let's declare some notation. We use semicolon, semicolon for doing sequential composition, colon equals for the assignments, and so on. And Andre's example is like that. It's a parametric program like that. You read some inputs, put in B, the value in B, then assign the value of B to A, and now you execute any steps. That's why it's parametric. It can be as long as you want. But each step is almost no op. You assign A plus A to A, and then A minus B to A. Basically, it doesn't do anything. A will keep the value B, right? So it's going to be 2B, 2B minus B is B again, right? And you execute that any times. And our spec, right, the post condition that we want to verify is given an initial memory, you are saying that the final memory, M prime, is going to be equals to the initial memory, no change to the memory. And there is some words that represents the inputs that we read. And the list of events contains these input events, and the local context, the value of A is V, right? That is equals to B. And we now define our predicate goal, saying basically if we execute this parametric program, right, for some n, any n, we're claiming that the specification will hold. Let's see how we'll do that. We're going to do manually for goal of size 1, right? This is our initial state for our problem. We can simplify it. It's going to expand the program. We can also unfold the spec. We can see the changes happening in the local context. This is the state of the proof. And we're going to start applying theorems, right? The theorems that we have seen before, like the continuation passing style for sequencing. We're applying these theorems, they mirror the structure of the program, right? We have a sequence of instructions. You're going to apply the first one, and it's going to transform the program. And apply each goal, each one of these goals we have here on the left-hand side is a meta variable in Lean. How apply works, when you see the theorem here, you see that it has many parameters. What a Lean does is create a meta variable for each one of them as a placeholder. And it's going to try to unify the conclusion with this theorem with the current state of your proof, right? It's going to unify these two objects. And any meta variable that has not been resolved by this unification process becomes a new goal. And this is the goal after applying the sequencing. Then we apply inputs, and you keep doing that. So introduce. Basically, so far we managed to execute the input P operation. Then we want to do the first assignments. We apply the sequencing again. We apply sets, but sets now is interesting. It creates many different sub-goals. One goal for the evaluation, where you have to show how to evaluate P, right? So remember that that's the expression you are trying to assign to A. And we have the post condition, right? With the local context updated. And you have the result of the evaluation, right? That is showing up here as a question mark. It is a meta variable. It has a goal associated with it. We first simplify the goal. It becomes V, the local, that's in the local context, equals to the V to the meta variable. You can solve by reflexivity and close this goal, not just the first one, but also the last one, that was the meta variable V itself. And now we can start executing this step. This step is just a macro I defined here on top. That is this two applies, the SymVC and raffle, exactly the steps we perform here. And we can keep stepping through, applying skip, and simplifying the proof is done. Of course, for a problem of size 1, I had to apply step twice, but for a problem of size 100, it's going to be 200 times. If we try to solve this problem using the Lean standard framework, tactic framework, it's called MetaM for metaprogramming, we get the same superlinear behavior that Andres warned us about, right? You can see the graph. It keeps increasing. It's not increasing linearly. And for 100, basically 200 instructions taking 2 seconds is too long, right? This is inefficient. It's not good enough. And why this example matters? Because the VC generators, these tools like Aeneas, Velvet from Ilya Sergey's group, and MVCGen by Sebastian Graf, they all follow the same idiom. They're applying theorems. And these theorems basically mirror the structure of your program. And so they will all exhibit the same superlinear behavior we are seeing right now. We just saw. What has to be fast to fix that? Well, apply has to be fast, right? We saw that we're applying using the static all over the place. The meta variable management has to be efficient. We have to be careful to not destruct term sharing. The terms in a proof assistant, they are not trees. They are direct acyclic graphs. And if you destroy the sharing, you can get exponential blow up. And SymM also has to be efficient, right? You have to reuse results across many different calls to SymM. Right? You don't want to keep traversing, trying to simplify the same terms over and over again. Sonho also mentioned one issue he had when using Aeneas. In this example, I did not use any fancy proof automation, but in practice, we're going to use statics like omega for linear integer arithmetic or grind available in Lean. And if your VC generator is creating many verification conditions, proof obligations, they all share a lot. They are not completely different. The initial hypothesis, they share many hypotheses. If your proof automation keeps processing, suppose it generates 1,000 goals and you have 1,000 hypotheses. Most of these 1,000 hypotheses are identical. If you keep reprocessing them over and over again, even if your procedure is linear time, you're going to get a quadratic behavior. And they are not linear time, right? I mean, they're way more expensive than that, right? So we have to share the states, right, between these different calls. This so was also in the Lean at Google Hackathon. That was another learning from this hackathon that we had to fix that. Okay, since then I started working on this new framework, right? Instead of using MetaM, let's use a new framework that's not general purpose. It's not meant to help fields medalists and software verification engineers at the simultaneously. Let's build one that's optimized for this kind of tool. It has additional constraints, right? Terms have to be kept maximally shared. And the whole point is to make this idiom, this flow that's applying terms, applying simplifiers, carrying the proof automation states around very efficiently. The first invariance is that we can rely on, we can declare that we are not, the local context can only grow monotonically. You can add new declarations to the local context. We saw in the example the local context increasing in size. You can add new hypotheses there. In the previous talk, you saw an example of goals with many hypotheses there, right? But we can assume that they only increase monotonically. We never revert a hypothesis. We never delete a hypothesis. And this framework will guarantee to you also that all terms are maximally shared. Right. MetaM, the default one, was built for arbitrary proof state surgery. This one is optimized for VC generation. For example, the process of assigning a term, no matter how big, to a meta variable. Now, the scope checks a constant time instead of linear time, right? And now, you may feel like, oh, linear steps are not bad. But the problem that they pile up, you are making a linear number of them. You get a quadratic behavior by just doing that. And people often say, oh, polynomial is great, but in practice, quadratic cubic time kills you, right? Especially if you're trying to verify a big chunk of code. All our terms are maximally shared, and SymM state also carries many different caches, right? About inferred types, universe levels, congruence information. Even it knows what's the maximal free variable occurring in any subterm. And this information is useful for optimizing the check when you're trying to assign a big term to a meta variable. Every operation preserves sharing, right? And by doing that, we make sure that we do not get an exponential blow up by transforming a DAG into a tree. Another point Andres made during the hackathon that I mentioned before that we have to unify the conclusion of a theorem with your goal. And in proof of systems like ROC, Lean, Agda, this process, this unification is modulo convertibility, right? Beta reduction, delta reduction, iota reduction, so on, right? Improving relevance. But this is overkill, right? I remember Andres always saying, it has to be syntactic, man. No way you cannot unfold anything, right? And SymM, the unification is very syntactic, right? There's no unfolding in the hot path, right? Moreover, the apply is pre-compiled, right? We saw in the example, you apply the same theorem multiple times. You can pre-compile information to make it as efficient as possible. Let's use metaprogramming. SymM is an API. It's an API that we already use it to build MVCgen, Velvet, and now IMEAs. But we can use it to solve our goal, right? We can create many for all the terms we use it in our example. we can create backward rules for them, right? And we have APIs for performing the introduction step, for calling the simplifier, executing the backward rules, right? Each one of these commands correspond to one of the tactics we saw in the previous example. And that's the cool thing. Lean is written in Lean, is extensible. You can write this piece of code in the same file where it is used. You can call solve here, and it will solve the challenge of size 10 for you, right? This is Lean code using the API that we are using for implementing MVC Gen, Velvet, and IMES, right? And okay, what happens if we use this small program to solve the challenge, right? Well, the first thing is not super linear anymore, it's linear, right? When you're competing with a super linear procedure with using a linear one, you can get as fast as you want, right? For n equals 100, it's more than 100 times faster. He cannot even get the meta M version cannot even get to depth 700, and the new one gets to 700 in 100 milliseconds, around 100 milliseconds, right? This is way better than what we had before. I put a link to the whole source code. You can play with it. What about SymM, right? It was not just applied. The example also used SymM. The SymM that comes to Lean, right? The SymM that MathLib uses extensively. There are more than 100 calls to SymM in MathLib. This is a general purpose tool. It's not optimized for VC generation. Each call to SymM starts the cache from scratch. It doesn't remember what it simplified before, right? The new one, it will remember, it remembers, especially, there's a caveat that I will mention later. But the most important thing that is also very syntactic, right? We don't want the fancy matching, the equivalence of a fancy unification with convertibility. We want it to be very syntactic. And we want to be able to go inside of binders very efficiently, right? Is a new simplifier for new workloads, right? And we use the same approach. I mean, Andres built this parametric example for us. We start using the same approach, parametric examples for checking how the simplifier behaves in different workloads. One thing that's the same way we have maximally shared terms, right? We can exploit these facts, and since all terms are maximally shared, you can cache results using the pointer, their pointers, right? You can hash the pointer, and this is your key, right? It's much better than computing dynamically a hash code for your terms. In this first example here, we have a term that follows this pattern. This is the version of size 5, where you have many nested functional applications. These things should be simplified, like 0 plus x, you want to simplify to x. Basically, what this example is testing is how the simplifier scale when he has to apply many congruence and transitivity rules to glue everything together. With the new simplifier, it scales really well. I mean, with size 5,000, it's 22 milliseconds. The kernel time is 46 milliseconds, and the proof size is also linear. It goes to 90,000 terms for a problem of size 5,000, right? Showing that you're growing linearly here is great. Binders, right? When you're verifying code, you have many binders, especially lets and halves, right? We want to make sure that this scales really well. If you have a barrage of halves, right? The first thing we want to preserve them. We do not want to expand them, right? We do not want to destroy the structure of what we are trying to verify. We want to preserve the halves. You want to be able to go inside them, simplify everything without a quadratic blow up. The new simplifier managed to accomplish that. I mean, for a block of 500 halves, it can do in 14 milliseconds. The kernel verification time is still not linear, but it's already good enough. It's 99 milliseconds for a block of 500 halves. But as I said, you have multiple kernels. This is the reference kernel we have. It's not linear, but as I said, it's good enough. The proof size is linear in this example. The simplifier actually is not a single tool, but a collection of tools. The main building block, we call it, is a SymProc, right? This SymProc is a simplification procedure, is a tiny building block that we put together. And you can use them for adding control. For example, if you have special support for simplifying if-then else's and match expressions, you can use this building block that we call simp control, right? Saying it's a simplifier for control flow structures. We have eval grounds. That's a simplifier for built-in types in Lean, like 2 plus 3 should go to 5, and so on. You have rewrites that you can apply theorems. And the simplifier is basically parameterized by 2 SymProcs. One called pre, that is executed before you go inside of a term, of the subterms, and post, that's applied after you visited the subterms, right? Basically, the main loop is just the engine to traverse the term, and it's calling these SymProcs that you provide as a user, right? Context-dependent caching is the next important point, right? Some simplifications depend on hypotheses, right? I mean, you may have a conditional rewriting rule, and this rule may depend on some hypothesis. And as I said, when we're doing verification conditionation, we're adding new hypotheses. Something that failed now may succeed later because you have new hypotheses, right? So your cache has to be aware of that. You can make this as complicated as you want, the cache management. We have a very simple solution. Most of the rewrites rules we use are not conditional. They are not context dependent. So we have one bit that we carry, just one bit. The bit says if the modification is context dependent or not. And we have 2 caches, one persistent and one transient. The transient is for the things that are context dependent. Most of the rewrites, we do go into the persistent cache, right? And this is great for performance. We don't have to keep rewriting this, visiting the same thing over and over again. And CBV. CBV is a tactic for simulating call by value. It doesn't rely on kernel reduction. In Lean, like in other proof assistants, we have something called native decides. But the problem of using native decides that you dramatically increase the size of your code base. Native decides now, if you use native decide in a proof, you're automatically relying on the Lean compiler. Now it's automatically in your trusted code base. LLVMs in your trusted code base, right? Our runtime is in your trusted code base. Lots of things are in your trusted code base now. Moreover, external checkers do not support all this machinery. If you use native decide, you cannot use an external type checker today. Maybe it will change in the future, but not today. But CBV allows you to do evaluation efficiently using this new simplifier. Was built by Wojtek at the Lean Flow. It produces a proof that can be checked in independent checkers, right? And you can have really fancy examples like this one that Wojtek created, that you get a string, you apply a sequence of operations. First, we split the string into slices. Then you filter the ones that are empty. Then you map these slices using a hash map that maps strings to the numerical value. Then you convert this iterate. So far it was we were using iterators. You convert to a list. You call merge sort. You map back by applying this operation that is going to map back the numerals back to strings. And then you create a single string finally by combining this list of strings in a single string by adding spaces. And it works. If you're trying to prove that this, by applying this function sort numbers to 6, 1, 2, you get 1, 2, 6. And it's not using native decides. It's using CBV that's proof producing, and you can check with independent checkers, right? Being able to execute codes in a project like Signal Shot is valuable, and you want it to be efficient. Okay, in the previous talk, they mentioned grinds. Grinds is a proof automation that Kim Morrison and I built last year. Has been released with Lean since 4.22. We are now in 4.29. Grinds is inspired by SMT technology, the same technology that tools like Daphne and Verus use. They use Z3 that I built too. But here, the main difference is Grinds is extensible. Grinds knows about dependency type theory. You don't need any translation to first order logic. And it's very configurable, right? But it follows the same idea of an SMT solver. You have a graph in the center where you collect all the equalities you learn into equivalence classes, and you have many satellite solvers like for linear integer arithmetic, commutative rings, orders, associative and commutative operators. And at the end, you get a proof that you can check with independent checkers, right? You do not need to trust the proof like when you use Z3. Let's see, SMT is all about theory combination. Let's see how it works in this small example. We have this cute example. I love this fact that if you have these three hypotheses, A plus B plus C equals C, 3, A squared plus B squared plus C squared equals 5, and A cubed plus B cubed plus C cubed equals 7, then A to the 4 plus B to the 4 plus C to the 4 is equals to 9, right? If alpha is a commutative ring. The ring solver in Grind knows that. It will learn that. And will propagate this equality to the graph that's A4 plus B4 equals 9 minus C4. It sends information to the whiteboard. Then congruence closure kicks in and lifts this result. Now it knows that these two applications are equal, right? The applications that are here. Then linear integer arithmetic proves it. It knows that 2 times something cannot be 1, right? Because f returns a natural number. So there is no way for this to be true and completes the proof. This is the Nelson Open playbook used by SMT solvers, but here it supports full dependence type theory, no translation to SMT, lib, or going to a first order logic, right? And every one of these solvers is parameterized by type classes. The solver for linear integer arithmetic is not just for integers. It can handle any type that can be mapped into integers. And the users can implement these mappings themselves. The ring solver is not just for the reals. It's for any commutative ring. It has support for commutative semi-rings too, for fields. If your ring has a characteristic non-zero, you can tell Grind it will use these facts. For example, here you have a bit vector of size 8. And we are proving that x minus 16 times x plus 16. Well, from high school, we know this is x minus 250, x squared minus 256, right? But a bit vector 8 is a commutative ring of characteristic 256. What it means, 256 is 0 in this commutative ring. And that's why this equation holds. And Grind proves it without using bit blasting. It's just using the fact that bit vectors form a commutative ring of characteristic 256. Right? You can add annotations to your theorems. They're like hints to grinds. This is a technique used in SMT, right? It's called e-matching. It's going to try to match your theorems, modulo equalities. I have a small example here showing how it works. I'm putting the annotation in this theorem here. I'm putting this annotation grids equals, saying you should use the left-hand side as a matching pattern. The idea is that if you find in your goal f of g of x, where x is something, right, is a parameter, you instantiate the theorem. You look at this goal, you may think, well, there's no f of g of anything. Well, there is one if you consider the equalities. You have f of a here, but we know that a equals g of c. Then morally, there is f of g of c, modulo equality there, right? And grind will instantiate the theorem for you. And there are many different mechanisms to control the instantiation. We are really excited that grind is one of the fastest growing tactics in MathLib. There are more than 4,000 occurrences of it since we launched last summer. But finally, we have what Sonho asked us. We want to carry the grind state around. You don't want to start from scratch. Otherwise, for every new goal, we're going to have to tell grinds about all hypotheses. You have to communicate this information to all your satellite solvers. You're going to have to fill their states with all this information, all the inequalities, all equalities, and so on in your goals. And your goals are very similar to each other if you're verifying a big chunk of code. We are going to carry the grind states. Your goal now, when we're doing verification condition generation, is not just a meta variable. It's the meta variable and the grind state together, right? I told you that SymM is a programmatic API. It was meant to be for tool builders like Sonho, right? But Andres made the point that debugging your VC generator by writing code is not great. He wants interactive modes, and we added interactive modes to SymM, right? When you use sim arrow, we are moving to the sim interactive mode, where this intro is not the intro in the default tactic framework. Apply here is not the apply of the default tactic framework, but they are the sim versions. And the grind state is being carried around here, right? But from the user's point of view, it's the same thing. You see this, you applied and intro, you see the two new goals showing up there. You can build, we have a GSL for you to customize your own simplifier, doing what you want. Each customization will have its own cache associated with them. And you can apply the simplifier here, you simplify your goal, you can call the linear integer solver. You may feel like, wow, you did all that just for Andres. I mean, yeah. We want Andres to be happy. But he also made the point in the future, he's not going to be the only user, right? AI will use this interactive mode. He made the point like when you have a looping variance, sometimes you want the AI to be able to see the state of the goal to decide which theorem it will apply next. Sometimes you can apply an optimized one. When we may be in a situation in the future where the AI is driving this process, right? MVCgen has been ported to this framework. MVCgen is the VC generator for monadic programs. Like in Lean, you can write programs using the do notation, is similar to the one in Haskell. This was implemented by Sebastian Graf, that's here today. And he mapped Andre's challenge was using a GSL, was a deep embedding inside of Lean, and he redid the challenge using MVCGen, but instead of using a deep embedding, a shallow embedding, using the Lean monadic framework, right? He encoded this example using monadic actions and verified them using MVCGen, and he gets linear behavior, right? Again, it's not quadratic, it scales really well. You can go to size 1,000, basically more than 2,000 assignments in less than 1 second, right? Velvet has been ported to SymM. Velvet is by Ilya Sergey Group. Vova, he showed up, it's Vladimir from in the previous slide. I mean, when you saw the collaborators of Beneficial AI, Vova is one of them. He's an intern at the Linfro currently. And Velvet is really impressive. I saw a demo of Velvet last year in Seoul. We are all attending PLGI. And Vova and Ilya demoed Velvet to me. I was blown away. But Vova came back saying, wow, the performance is not good. I mean, it's much lower than Daphne. And matches Andre's observations that tools that have a large trust code base scale better. But since then, Vova redid Velvet. Is Velvet with Loom 2, is the green bar. And basically is already outperforming Daphne in 24 of the 27 benchmarks. The remaining ones actually is not Velvet's fault, it's Grind's fault. We're going to have to improve that at the Linfro. But the very encouraging thing here is that here we have Velvet has a very tiny TCB, right? And is outperforming a tool that has a really vast TCB, right? Daphne, Z3 is there. I mean, Z3 is 500,000 lines of codes, right? I mean, and you cannot check the proofs produced by Z3 with the confidence you can with the proofs produced by Lean. The VC generation itself, you do not have to trust, right? Okay, I mean, AI, it's impossible to give a talk these days without mentioning AI. It was not, like, I did not combine with Max, the zlib. I just suspected he would mention it. These are experiments that blew my mind. I mean, it was Kim Morrison. He works with us at the Linfro. He has been in the Lean community for 10 years. Kim asked Claude Codes after writing a detailed plan. I mean, Kim wrote a detailed plan explaining what zlib is, telling Claude that you should convert the code to Lean, ensure the code passes the test suite, and only then try to prove that if you compress a file, compress data at any compression level, and you decompress, you get the data back. Basically, you're proving the round trip is correct. 6 months ago, I would say this is a pipe dream, no way this can be done, but the AI did it after 1 week. Came exhausted. I think burned many tokens doing that, but it succeeded. I mean, and you can see Kim's experiments at this link, LeanZip. I got jealous, I mean, of these experiments, and I came up with my own, I mean, a version. I asked Claude to implement a DSL, much more complicated than the one we have seen. This one with function calls, dynamic memory allocation, control structure, breaks, and you name it. It's not fully autonomous. I had to guide the whole process, but in natural language. I did not write code. I only guided Claude using natural language. For example, the spec was wrong. I had to tell it to correct the spec. When it proved the interpreter correct with respect to the spec, he declared victory after he proved completeness. I said, where's the soundness proof? Then these AIs feel like they are human sometimes. They say, oh, yeah, I forgot about this. Yeah, I'm going to do it now. I mean, they are lazy sometimes, it's crazy. I mean, you have to say, come on, where's the proof is missing? And it did it. But for me, the fact that I was working on something else and from time to time giving some directions in natural language was really cool. I mean, and I put a link to the whole experiment here, the source code. But before this happens, I mean, another thing that's now everybody takes for granted is that AI can solve IMO problems. Oh, sorry, this is touch sensitive. Now everybody takes for granted that AI can get medals in the International Mathematical Olympiad. But in January of 2024, people are saying, no way. This is BS from AI companies. This is impossible. This is never going to happen. And it happened 3 times already, right? Alpha Proof from Google DeepMind using Lean got a silver medal. Then last summer, Aristotle from Harmonic and Sid Prover from ByteDance also got medals, right? All 3 teams used Lean, right? And that now there are many startups. I mean, Axiom solved 12 of the 12 Putman problems from last year. DeepSeek performed really well. The mini F2F tests. It's incredible. None of these systems existed at the beginning of 2024, right? Then a question is, do we need automation? If AI is getting so good, do we need automation at all? Let's say AI do everything. But it's what Sonho says. I mean, we have many VCs sometimes for a complex piece of code. You're going to generate thousands of verification conditions, right? Most of them are trivial, right? We want to discharge the trivial ones very efficiently. And AI can't compete, at least right now, it cannot, right? Another thing is that it's embarrassing, but in this automated to improving, that's my real community. There's an embarrassing part. There's the part that we are all proud of, that is the algorithmics, the data structures. But there's the embarrassed part that's heuristics that are hard-coded in your solvers. There's no science there, right? It's like black magic, right? These heuristics. And I think AI can do the black magic much better than us, right? Basically, what I'm saying is that the algorithmics, the data structures that are the fun part will stay, but the black magic will be taken over by AI, right? You say, we want grind to be fast and dumb. No fancy. He's applying the algorithmics very efficiently, discharging all the easy goals very efficiently. And the ones that we cannot do automatically, let the AI do. Do not try to hack another crazy heuristic. Trust. Trust is really important now. I mean, so far we have been facing adversarial users, right? They really are trying their best. They're not trying to deceive anyone. They're really trying to prove. But AI, like Terry mentioned, will exploit anything to achieve their goals. Right? Doing the reinforcement learning, they're trained to achieve the goal, no matter what, right? And if there's unsoundness in your system, the AI will exploit, right? Tools with a large TCB are liability now. We cannot assume the users are not adversarial, right? They are adversarial. They will try to exploit any unsoundness bug in the system. In Lean, we take that in layers, right? So we have the everyday use where you're using your IDE, right? Lean is extensible, you're running meta programs there. Someone can write a meta program that corrupts your memory, right? That bypasses the kernel. This is good enough. The everyday use is good enough for someone that's not adversarial. You can completely eliminate the threats of meta programs by using the lean4 checker. Lean4 checker is an independent tool that will check everything for you without running any meta program. It's just the kernel. And you can go beyond that using comparator. Right? Comparator was built by Henrik. He's here. Henrik Boving, he's here today. Oh, he's over there. He builds comparator that will export your proofs. He constructs them in a sandbox, right? And you can even use more than one kernel. You can read more about trust in our FAQ in our website. But we have to keep in mind, trusted code base is a liability. Tools that rely on SMT solvers or have use VC generators that are not verified. This is a large surface, right? We can minimize that. And one point I like to make that the Lean compiler is not part of the TCB for the signal shots. The compiler is in the TCB only if you're using Lean as a programming language. For example, in the Lean zip experiments, Ken mapped zlib from C to Lean and prove the Lean version is correct. You want to execute this Lean zip code. This code, the Lean compiler now is part of the trusted code base and LLVM and our runtime. But for signal shots, we are not using Lean as a programming language. We are using Lean as a prover, right? The programming language is Rust. And being able to check with multiple independent kernels is key, right? I mean, Joachim Breitner, he's also here today. He built arena.leanlang.org. It's a way to motivate people to build new kernels for Lean. In his arena, we have the reference kernel in C++. We have the Anoda, the one written in Rust, Lean for Lean, written in Lean itself by Mario Carneiro. I think there is a new one. I think it's Nano something that Joachim wrote, and it has amazing performance results that's there also. And we expect many more will show up, right? And this is great. Any disagreements between them exposes something that we should focus on. Lean4 checker, I already mentioned it. And the comparator too, I can skip quickly. But one thing I want to emphasize before we end, we have to be crystal clear about the TCB for the signal shots, right? Especially because I believe this project will attract a lot of attention to our communities, and people will scrutinize the results. Many people believe just because a prover checked something, it's correct. But it's correct with respect to the specifications. We have to keep repeating over and over again the specifications are important. Verilib will play the role of showing to the general public what the specifications are, right? This is important. We have to make clear to everybody that Caron and Aeneas are part of the TCB. The Rust compiler itself, we may do all our parts. Our specifications are beautiful. Caron and Aeneas, we checked manually everything checks. But if there is a bug in the Rust compiler, it may validate the whole effort, right? We have to keep communicating to everybody the TCB. This is not like removing our credits, right? It's increasing it. We have to be transparent. Our commitment to Lean Flow is we are committed to ensure that Lean scales for the signal shots, right? We will add missing proof automation. I mean, Oliver, Sean already have their list of things that we need to implement. We will do it. I mean, we are strong to we really want signal shot to succeed. Okay, the conclusion, yeah, Lean is a platform that scales and is ready. SymM and the new simplifier turn a superlinear bottlenecks in linear ones. Thank you very much for your attention.
Thank you. Leo, are there questions? Leo. Yes, please.
What does the SYM stand for in SymM?
Because it's
So
because
perhaps
Andres.
You can repeat the question for the
Okay, what the SYM stands for in SymM? Because Andres kept saying during the hackathon, this symbolic simulation, that it comes from symbolic. That's why.
There are other questions. Yeah.
So it's really interesting talk. I have a question about data action between Lean and Python, which is currently not so developed. Because now we are the Beneficial AI Foundation, we're focusing a lot on Rust, which is on production code. A lot of AI models, which is what we're ultimately interested in Python, right? Which is a much messier, high-level language. So I wonder if you have any hopes or aspirations to somehow merge Lean and Python in a way, maybe do something like an Aeneas tool for like a subset of Python. Do you think that's something that would be worth pursuing? What is your opinion on that intersection?
Perhaps you can repeat the question again.
The question is about Python and Lean, if you're going to have support for Python. For pure Python is enriched, but if you really want to analyze arbitrary Python codes, then it's tricky because arbitrary Python code is using, for example, a bunch of code that's written in C, like PyTorch or NumPy. And in the near future, I can see us adding specs for these modules and saying, believe me, that's what these things do. But it's a much longer term project.
Really excited.
Yeah.
What's the status of post-Lean?
Good question. I'm trying to find out. I don't know. But I will reach out to the main developer. We know him.
There was another question there. Yeah.
Yeah, you talked, maybe I missed this, you talked a lot about sort of the scalability problem and that was at sort of like the lean source level. But what about the size of the kernel proofs? Is that also something you've been looking at?
Yeah. We had some. We have some data, right? We had some slides. I put data of the size of the third graph is this.
So that's for the kernel proof.
Yes,
that is
exactly.
the kernel proof.
Yeah.
Not for the.
No. No, actually, it's super small. The code that creates these proofs.
Okay.
Thank you. Yeah. One
So
question.
what are the limits for SYM? What other program logic does it work for? Probabilistic, relational, separation logic?
Oh yeah, SymM is the infrastructure, right? That you build tools like Velvet, MVCgen, Aeneas, and so on, right? These are the tools your question is connected to these tools, not SymM. SymM is just the APIs. It's how Andres likes to say, apply simp intro really fast. The logics on the tools on the next level is on Aeneas. Yeah.
So perhaps just a slightly related question. So grind and SymM. So have you re-implemented grind?
No, it's just connected.
It's connected. So,
yeah, refactored. To being on top of SymM.
Okay, so now you can use grind within SymM.
Yes,
okay.
Exactly.
Okay. Was perhaps one last question because then we have the break.
The SYM interactive mode is really cool. Thank you. When you do apply that SYM interactive mode, you get the freaking how feature that you were describing earlier.
Yes.
Very
yes.
cool.
Yes. Yeah.
Okay, thank you very much. So we are first of all thanking Leo again